It is May 19th at approximately 8:18 a.m. Going to be going over the first part in a 12-part series on the history of mathematics using the textbook A History of Mathematics by Merzbach and Boyer. So, to start us off, just start with chapter 1. Traces of what? Well, let's go back 3000 BCE to approximately 4000 BCE. And so we're going to be looking at the emergence of numerical intuition amongst hunter-gatherer societies. And this will actually be quite basic, as you can imagine, because these things are basically going to be rudimentary tools by which we can map our memory onto objects. So, for example, there's this thing called the Ishango bone that archaeologists think originated around 22,000 BCE. So basically what it looks like is this bone that has these tally marks in it. Now, we could just think that perhaps these things are random. Random, don't make any sense. Perhaps somebody's just fidgeting with what's left over of their meal, right? But this may not exactly be the case, because a hunter-gatherer group wants to track lunar phases for rituals or hunting, for instance. You need to know exactly when you're going to hunt, what exactly is going to be there upon fertile grounds. So, they mark a bone or a stick each day, over time, beginning to group the notches, perhaps in 5s, perhaps in 10s. Nothing like the one that I just portrayed right here, but that's just an illustrative analog. What's interesting is that this bone that was picked up back in, it's roughly 24,000 years ago. What's interesting about that is it shows notches arranged in what may be primes or lunar cycles. So this is exactly what they were doing. Birth of arithmetic as external memory. This idea that you can't exactly hold in your mind all of the many numbers you can't exactly hold in your mind all the days, all the weeks, all the years, all the different times by which you have the best or the most ripe opportunity for hunting specific animals, looking after your tribe, etc. But turning away from something a bit more carnivorous in the case of hunting animals, going into that more gathering part of hunter-gatherer societies, let's ask ourselves a question. You're one of these primitive peoples and you want to know, how do I tell if one pile of berries is equal to another? Simple enough. Two foragers want to compare piles without counting. Not really, because numbers haven't exactly been invented yet. But you can use one-to-one matching. You can pair each berry from one pile with a berry from the other. Let's just use pluses and minuses, because why not? Because that's on my head right now. From each berry until the other runs out. This is a sort of proto-cardinality, the core of set theory. Before they knew what Three was they knew what equal meant. You look at these two shapes, well, there's no language of two really, but you can look at that and say, oh, these look roughly similar, and it's not exactly like this one over here. That's pretty plain and simple. And say you want to know how exactly, you want to keep track of the people around you. You want to keep track of the people that are in your tribe. How many people left the camp? Suppose 10 warriors leave the village. How do they confirm they all return? Well, there's pebbles, there's sticks, there's all sorts of things. There's all sorts of things laying around that you could use to represent these warriors. So you have 10 pebbles or sticks, remove one for each departure, place one for each return. Full pile equals all returned. So they all made it back home from fighting whoever, doing whatever brutal thing they did, or peaceful thing, though they were warriors. This is the abstraction of identity, a symbolic representation system. You know, you hold up a finger, there were one of them over there, there were two of them over there, there were three of them over there. Simple enough. Now, suppose you're one of these tribes, and you kill a large boar and need to divide it among 3 families. Now you can slice this into 2 equal parts. Let's just draw our boar here. Not exactly the best looking creature, but that's fine because it won't be around for long. So you kill a large boar and divide it amongst 3 families. You slice this visually into equal parts, discovering symmetry and equivalence. It's essential that nobody's cheated. It's essentially that nobody thinks that they've been done wrong. But you want to separate this into 3 separate pieces, you know. So you're going to be thinking about these ideas. That's not 3 different pieces, but the idea would be more so to belong here or something like that. But you get the idea. This is the sort of thing that they can't properly articulate, that wasn't properly articulated insofar as we know. But in the idea of fairness, you know, even animals will recognize whenever they're cheated. There's some videos out there where you give some food to one monkey and you abandon the other completely, and the other one will start freaking out because there's some sense of fairness, perhaps, even in the natural order of things. So this becomes foundational for division and fractional thinking. Now, another thing that's practical, another thing that you could run into within this primitive society is the matter of designing a basket that doesn't collapse. Suppose you're trying to carry grains or berries or parts of a wild boar that was captured earlier in the day. You want to transport it from one location to the next. Then you're going to have to figure out how to weave stronger patterns than other instances. You can't just, you know, well, you could overlap. You could just make one line, and that wouldn't exactly be efficient as the overlapping weaves. You could use repeated geometrical patterns like triangles and all that jazz to reinforce structure. They didn't draw triangles, they didn't draw these weaves, so to speak, so much as they lived inside of them. These were just things that you did in order to lift things. If you sort of MacGyver any sort of rigmarole, then, you know, quite naturally you can see how the primitive people must have thought. So what does this mean for the folks living in this time period as regards the history of mathematics? Well, It's not exactly a thing that's properly articulated, not exactly a thing that's thought into one cohesive ideology or study or body of knowledge. It's just sort of an afterthought of practicality, something that you could see later on when hindsight is 20/20. So let's move on to a more complex notion of society arising in ancient Egypt. Turning to chapter 2, which, aptly enough, is called Ancient Egypt. And time to do a routine checkup on the camera to see if everything's going okay. Yes, okay. So the approximate range for this is, I'll just start putting BC because why not? (2700 BC to 1600 BC, and let's even specify this to time of the Old Kingdom, from 2700 BC to 2200 BC, so a long, long time ago, with the construction of the pyramids of Giza. And the use of land surveying. Probably not the first, but one of the earliest recorded instances for tax purposes, because, as everybody knows, there's only two things that are certain: death and taxes. Nah. But, so we have that time for the Old Kingdom, and then moving on to the Middle Kingdom, around 2000 to 1650 BC. We'll go into talking about these two papyri, by which we know what happened. So, this is our timeline, this is what we're working with. 2700 BC to 1600 BCE, primarily the Old and Middle Kingdoms of ancient Egypt. They're going to be using unit fractions, additive decimal systems, false position methods, practical geometry for agriculture, taxation, and architecture. So let's get a better look at exactly what sort of landmass we're working with here. So, as many of you likely know, or hopefully know, Egypt is kind of this, well, it's this country nowadays in the Middle East, and has this long, winding river called the Nile. Called the Nile. I'll just label this Egypt. The Mediterranean Sea is over here. The Red Sea is over here. Early civilization goes along a river there. Makes sense enough. Let's see what this means for the future of mathematics, for the past of mathematics. Developing out of this Nile region, which is subject to rapid instances of flooding. So, Let's say this Nile, this river, this gift and curse that gives us both life and death, floods, and it erases all our former farming boundaries. What do we do now? Well, after a flood, suppose a farmer claims 12 square rods of land. Now, this is just their way of measuring things back then, not exactly subject to the imperial or metric systems, respectively. A farmer claims 12 square rods of land after the flood. After flood. Now, scribe, likely for taxation purposes, let's verify this using geometric calculation. So let's look at the area of the land that he does have and check if what he's saying is true. We look at the base of his land and we find it's about 6 rods and a height 4 rods. Now the Egyptians had found the way to find a triangle area by this point, 1/2 base times height. But there's also this rather interesting doubling table method, which pops up in ancient texts, which I find rather fascinating that they stumbled across. Whoops. Six equals to 2 is equal to 2 plus 4. 8 plus 16 is equal to 24. 24 over 2 is equal to 12. So it kind of has that sort of, it's an algorithm. It's essentially an algorithm by which you double. There's another word for it that I'm missing out on, but yeah, and you get your answer there, and it follows the pattern as you can see here, and it works inefficiently in comparison to something like a formula for the area of a triangle, but is accurate, and accuracy in ancient times is something definitely to be praised. Now, suppose this. The scribe must compute 17 times 23 using Egyptian multiplication by doubling. Suppose this could be for troop formations. You want to know exactly what your armies look like, how many soldiers you have, so you can write it down in some scroll or some wall that you'd keep for posterity. Or just for logistical purposes. So, you're stuck in ancient Egypt and you don't have the advantage of modern mathematics to help you. Whatsoever will you do? Well, turn back to the Egyptian method of doubling using a doubling table. One 23, 2 46, 4 92, 8 184. 16, 368. So from there, see that 17 is equal to 16 plus 1. From there, you see that 368 plus 23 is equal to 391. So, there are 391 soldiers to account for within your Egyptian army for logistical purposes. Let's go ahead and make arrows. Make that look a bit more pedagogical. Now, something that the Egyptians are quite famous for are, of course, their pyramids. Suppose an architect needs a pyramid face to rise 7 cubits vertically for every 70 hands, which is equal to 10 cubits of horizontal run. So you need pyramid face to be 7 cubits vertically for every 70 hands. Of horizontal run. So what's interesting is the Egyptians did actually have a notion of slope, but it was reversed to what we currently understand as rise over run. So they had this thing called the set, if I'm pronouncing that right. Running hands over rise in cubits. So with that in mind, you of course get that the sect is equal to 10. So what does this mean? What it means is the pyramid face, it slopes inward. Inward 10 hands for every cubit of height. So you have a prototypical version of the slope, used for something as grand as pyramids. Now, as I promised, as was said earlier, taxation is something that runs to the very core of every civilization, including the earliest. So, suppose a tax collector takes 1/7 of a pile. What was the original heap? The original heap So the Egyptians had this interesting system by which they would guess numbers that seemed valid by an algorithm that would lead to a sort of prototypical version of numerical approximation. Guess that x is equal to 7 such that, such that x plus 1 over 7 times x is equal to 7 plus 1, which is equal to 8. They have this notion of a scaling factor. So they'd scale the guess case, 2.375 to get x is equal to 7.2.7 times 2.375, which is equal to 16.625, which is equal to 16 5/8, 5 over 8. So they'd scale the guess here, and this was sort of just a run it through and check exactly what it looks like it could be. And so in this case, they get that the scaling factor, sorry. They take the scaling factor, which they have here, which they just thought should be 2.375. So that gets us 16.625, as I mentioned earlier. Now, to account for this sort of shot in the dark, in a way, an estimated shot in the dark, a shot in the dark nonetheless, they have these methods of checking it. So, which is essentially just, let's plug it back in and see if it gets the number by which we divided by 8. Well, not always 8. Oh yeah, sorry, I forgot to mention that this is essential. A heap and its 7th, that's essential, is equal to 19. Heap and its 7th is equal to 19. And then we had to find the original heap using this method of false position, which, as I mentioned, well, is this guessing and checking. This guessing, scaling, and checking. So, 16.625 plus 1/7 times 16.625 is equal to 16.625 plus 2.375, which is equal to 19. So the Egyptians would see that, and they'd say the original heap was 16.5 over 8. Of course, they wouldn't say it in English, they'd say it in Egyptian. So let's move on to our next ancient civilization, rather region of civilization, within the Fertile Crescent. This being Mesopotamia. The approximate range being from 3000 BC to 1600 BC. Three civilizations mentioned within this chapter. Sumerians, the Akkadians. It's interesting because sometimes you pronounce it Sargon of Akkad. It's Akkadian Empire. And the old Babylonian period. From 3000 to 2300 BC, 2300, 2100 BC, 2000 to 1600 BC. And what's interesting is, thematically speaking, we have different cruxes by which mathematics emerged here. So this is mainly tokens, and we get early number systems. For the Sumerians, administrative expansion. So it's just going to be basically taxes for these guys. Not sure if you can actually read that back there. And we'll get the peak of mathematical activity in the old Babylonian period. For these folks, we'll be looking at base 60 positional notation, reciprocal tables, root approximation, quadratic equations, and geometric computations. Now, the guiding premise for talking about mathematics in the Mesopotamian region in this time frame is that mathematics, it's not exactly as doesn't exactly carry that weight of financial essentialism that the Egyptians have. So with the hunter-gatherer societies, you have this notion of banking your memory, tallying on bones and such. And the Egyptians, you have how exactly do we manage taxes whenever things flood? How exactly are we going to build these great pyramids for the gods? For these Babylonian folk, for these people in the Mesopotamian region, it's not exactly born of curiosity per se, which we'll see later, though with any sort of invention it has to presumably be within the mind of someone at some point at some time. But from contracts, clay and cosmic patterns, I recall an instance where there was this thing over social media where everybody was talking about this copper trader. Back then, whenever you wanted to write a bad review, you'd take out a tablet and you'd have to etch it. And for what might have taken a few hours, this person just wrote exactly how terrible they thought certain copper merchant supplies actually were. 6-hour-long bad review, basically. So this notion of contracts, clay, and cosmic patterns, you can kind of see what world we're stepping into whenever we try to look at mathematics in ancient Mesopotamia. But there's still, of course, as there always is, the weight of financial essentialism. So suppose you need to split 34 minas of silver among 5 people. Suppose, for instance, a merchant must divide 34 minas among 5 different partners. There's no long division. There's no instance of division to speak. But what you can do in this time period, what you do know about, something that has been conceptualized, is this notion of using reciprocal tables. Can't divide, we don't know what that means, but we do know that we can multiply by 1/5. 6.8, which is equal to 6 semicolon 48 in sexagesimal. This is what they used for their number system. The semicolon here, we'll get into this notation a bit more, but it's what they used, so I'm going to be covering that and showing its equivalency to what we use nowadays. Of course, sexagesimal being that base 60 approach to numbers. So Babylonians preferred multiplication by reciprocals, a shift from division to algorithmic computation, which is interesting because you see it later in modular arithmetic as things tend to get pretty wonky in modular arithmetic whenever you try to divide things. But that's for another day. So 6.8, you divide 6.8 minas of silver among 5 people. I suppose you'd keep 1 to yourself. I don't know. Depends on exactly how desperately you need it. So, let's move on to another problem which they might have faced. Let's suppose an astronomer priest of this ancient time wanted to record time and angle fractions for planetary movement. And you're stuck here, and you're using base 60 positional numbers because, well, let's see. So, how do I write an hour and 30 minutes? How do I write that as passing by? So with base 60 positional numbers, you can represent an hour and 30 minutes just like that. 1 semicolon 30. What does that mean? Well, translating that over, 1 plus 30 over 60. Which of course is equal to 1.5. And this is a number system which persists in clocks and circles. So efficient was it back then, so we use it now. And they didn't choose the 60 for beauty, they chose it because it plays nicely with division, at least dividing the numbers that they were working with at the time. So you again see this notion of practicality, this sort of, we go towards the abstract simply because the abstract gets us things that we can use practically speaking. And another such instance of that, suppose an engineer designing a ramp or a ziggurat ramp, or ziggurat ramps, needs consistent slope and right angle reliability. King wants a right triangle ramp. What's that diagonal going to be? You need the ramp to build something, perhaps. Perhaps a pyramid, though they weren't really building those in that area. Well, what's interesting is that we have this document called Plimpton .322. Now, within Plimpton .322, we find that these Mesopotamians had the notion of Pythagorean triples. way before way before Pythagoras ever came about, way before the Greeks were really touching this sort of stuff insofar as any of our historical records are concerned. So you use Pythagorean triples to help you build these ramps. Like so. They use Pythagorean relationships without formal proofs. Geometry by example, geometry by trial, rather than geometry by formalism. They didn't draw right triangles, they walked them. You sort of see the pattern there with the hunter-gatherer societies. They didn't think about drawing the weaves, the interlapping weaves, and think about a bunch of physical equations or physical mapping equations or anything like that. They simply didn't. It's this notion of simple practicality. And again, let's turn to another example of this. A land grant must be divided under complex restraints. Let's suppose we have a legal condition for this land grant. So it's absolutely ridiculous if you think about it and think, well, contracting. But again, the ways that land can be divided up, you gotta think, it's gotta be at least one instance when something like this had to have popped up, or something similar, maybe a bit more simple, but for the sake of just elaborating on this, let's take a look. A legal condition by which this is equivalent to 1 mina. That's their form of currency. How would you go about doing this in ancient Mesopotamia? Well, so y is equal to x plus x over 7, which is equal to 8 over 7x, 12 over 11y is equal to 1, and this implies that y is equal to 11 over 12, which implies that x is equal to 77 over 96. What exactly is this in sexagesimal? Base 60, 0, semicolon, 48, 7, 30. So you can see by algebraic manipulation the cleverness of getting this answer. And this is algebra through verbal logic and scaling. It's pretty symbolic, but it's structurally sound. Before they had x's and y's, they had proportions, portions, and heaps, and they solved it just as well. So let's turn to another example of something that they would have known about in this time and in this place. Suppose a land surveyor needs the diagonal to stretch rope across a square plot with side length 30 units. Well, here's something interesting. You want to figure out this here across a square plot. side length of 30 units. Well, what's interesting is we actually have the approximation that the ancient Babylonians used for the square root of 2, which is shockingly close. Well, for ancient times, it's pretty good, which is roughly equal to 1.4142196. So they take that, then they multiply 30 by that square root of 2 to get 42.42639, which in base 60 or in sexagesimal is 42 semicolon 25, 35, 49, etc. Now this is precise irrational approximation via algorithmic tables. So you think there used to be this thing that people did before they had calculators, really, where engineers would use these tables of numbers. It's kind of like that. And these are some of the pieces of evidence that we found of Babylonian arithmetic. They built right-angled space with the square root of 2. And they didn't exactly have a need to name it. This is, of course, it's just our way of representing it. This is a way of representing it. But what they actually had was just, well, we can look at that, and if we multiply it by that, we get that, and that seems to work. And so they just kept using it. No need to name it. It just sort of falls into the background. Babylonian math was table-driven, abstract, deeply practical. Base 60 enabled clean divisions and wide computational flexibility. They pioneered algorithmic thinking centuries before symbolic notation. So to conclude, let's go ahead and talk about what the gives and takes were throughout time, throughout these early years of mathematical thought. Mathematics did not emerge fully formed, of course. It grew over time, through abstraction, formalization, and cultural need. Each stage of mathematical history reflects a conscious or unconscious sacrifice of the immediate, the concrete, or the ritual in exchange for something more abstract and powerful. And you see that with each iteration that we're looking at here. Some existing at the same time in the case of Egypt and Mesopotamia, but the point still stands. And we can see this with prehistoric humans, giving up the purely instinctual, context-bound perception of quantity, gaining the concept of number through contrast and sameness, gaining the abstract thinking rooted in physicality, with fingers, notches. Mathematics is a tool of memory, ritual, and pattern recognition. They gave up immediacy and gained the first glimmers of abstraction. We moved on to the Egyptians, and we found that they had given up a loose, oral, and purely concrete method of counting and measuring. Not completely, everybody still uses tally marks, but as a main thing, dependence on myth and ritual to structure number relationships. And as a result, they gained a formalized arithmetic and geometry, recorded in writing, unit fractions, area and volume formulas, and the method of false position. The mathematical culture stood rooted in administration and practicality. They gave up the mythic and gained the measurable. And then turning to the Mesopotamians, who I have erased from the board, they gave up the rigid, symbol-heavy, additive systems to sole focus on concrete or empirical problems to gain to gain a contingent of methods by which they could solve future problems. A base 60 positional number system with powerful fractional capabilities, algorithmic approaches to roots, equations, and interpolation, generalized table-driven, and abstract computational strategies. They gave up repetition and gained recursion. They gave up tallying and gained theory. So to sum up, the prehistoric peoples, they named quantity. The Egyptians measured the world. Mesopotamians began to calculate the abstract. Each civilization gave up something tangible to gain something powerful. As mathematics grew, it became less visible, but more universal, evolving from physical objects to mental systems, from stone to symbol.